Hi, welcome to lesson 7.4. This is our fourth section in chapter 7, and it's the second to the last section. And this is all about writing and graphing exponential growth functions. And you'll see what we mean by growth here in a minute. But this is exponential growth functions, and we haven't dealt with exponential functions yet. So you'll kind of see how it works. It's not super difficult, but it kind of goes with what we've been doing with learning about exponents. All right, before we do that, go ahead and pause the video after you do the warm-up, or pause the video, do the warm-up exercises, and then check your answers. We're just changing percents to decimals. Okay, hopefully you were able to change 2% to 0.02 because this means 2 per 100, and this means 5.5 per 100, so it's 0.055. If you have questions, you can ask. But again, it's just moving the decimal 2 places to the left. And here's our vocabulary, okay? An exponential function is just this. It's a function in the form y equals a times b to the x power, where a is not 0 and b is not 1, okay? If we have a equal to 0, every time, no matter what x is, 0 times whatever b to the x power is, we'd have 0. We'd have no function. It would just be y equals 0 every time. And if we have b equal to 1, we end up with y equals a. So we end up with just a linear function at that point because 1 to any power is just 1. So here we have no function, and here we end up with a linear function. So if we truly want an exponential function, a cannot be 0 and b cannot be 1. And an exponential function is nonlinear. We have been used to having y equals something x, something times x. In this case, our x is now the exponent. So our unknown becomes our exponent. But this right here is kind of the key thing that we're going to be doing in this section and the next section as well. We're going to compare an exponential function to a linear function and how we can kind of tell which is which. So as we look at this table, and as we see, we go from -2 to -1 to 0 to 1 to 2. That's what the x values do. So as you can see, the x values are increasing by 1 every time. And if we look at the y values, we go from -4 to -1 to 2 to 5 to 8. And so as you can see, the y values are increasing by 3 each time. So if you look at this table shows a constant rate of change. It's linear, okay, and it has a rate of change of 3 over 1. For every increase in the x value, our y value increases by 3. This next table down here is a little different, as you can tell. We've got some weird fractions and different things. The same thing happens here in the x part of the table, though. It's increasing by 1 each time. Down here in the bottom, though, you'll notice the y value is not just increasing. Like right here, we're adding a half. We're adding a fourth, but then here we're adding a half, and then here we're adding 1, and here we're adding 2. So we've got to find something that's kind of the same, but there's no constant increase or decrease. And so since there's no constant increase or decrease, we have to look at another operation of what's going on. And sometimes it's hard to tell that with the fractions. So if you'll look from your first fraction into your whole numbers, it kind of helps you to see that if we multiply 1/2 by 2, we get 1. And if we multiply 1 by 2, we get 2. And if we multiply 2 by 2, we get 4. So we want to have the same thing. We want to be doing the same thing to our table, but it's multiplying by 2 versus increasing or decreasing by 2 or anything like that. So there's our kind of our constant rate of change. However, since we're multiplying our y values, but we're only adding on the x values, this is an example of an exponential function. So there's the difference. Okay. All right, so here's our first example of writing a rule and how we're going to learn how to write the rule. So here's our table, and it says write a rule for this function. Well, first of all, we want to look and see whether the function is exponential versus linear. So in other words, are we increasing or decreasing by a constant rate with both x and y? Okay, so let's look at this. Okay, so let's look at our table. And our x is increasing by 1 each time. But down here, our y is not increasing by a set amount each time. We go from 1 over 11 to 1 to 11 to 121. So I want to look at this. We're multiplying by 11, multiplying by 11. So as you can see, that's our pattern. So the y values are multiplied by 11, which it says right here, for each increase of 1. So the table represents an exponential function in this form. Please get to remember this form, okay? And how your y values are changing, the multiplication effect that's going on here, that becomes your b. b equals 11. So if we were going to write this, we could write this as such. A times 11 to the x power. Okay? Now we still don't know what a is. We have to find what a is. But at this point, we don't know what that is. So now we just have 11, a times 11 to the x power. Here's how we find what a is. Here's step 2. Okay? We want to find the value of a by finding the value of y when x is 0. Because when x is 0, that means our b to the 0 power is 1. So y equals a when x is 0. So let's find what a is when x is 0. So here's x at 0, and here's y when x is 0. So a must be 1. Okay, and that's what it says right here. A equals 1. And then step 3 is to write it all together like that, right here. Y equals 1 times 11 to the x power, or we could just write it like this. Y equals 11 to the x power. And that's an exponential function, okay? A may not always be 1. A might be something else, but that would be the case right here, okay? All right, example 1, guided practice. So I want you to try to find the pattern. Remember, what you're multiplying by each time becomes your b, and a is where what y equals when x is 0. So pause the video and try. Hopefully that's what you came up with. Okay, example 2. Graph the function y equals 2 to the x power. Identify its domain and range. Well, obviously, we're going to be making a table with some values. Choose a few values for x. Keep it simple. And the domain is all real numbers. We're going to tell you that any number can be x. Remember, the domain are your x values. What values make sense for x in this case? Well, in this case, any number could be x. We don't have any restrictions, so all real numbers. So let's make a table of values. We went from -2 to +2, and here's basically what you're doing. Y equals 2 to the -2, which is 1 over 2 to the +2, which is 1/4, okay? And then we do y equals 2 to the -1, which is equal to 1 over 2, or 1/2. And then when x is 0, 2 to the 0 power is 1, 2 to the first power is 2, and 2 squared is 4. So you can kind of see how easy it is to make those table of values. And now, obviously, step 2 will be to graph those points. So here's our points. We have -2 and 1/4, -1, 1/2, 0, 1, 1, 2, 2, 4. Notice this is going to be a curve, and it is going to rise very rapidly. Going to rise up very rapidly. I also want to point out, as close as we get to the x-axis, this will never, ever, ever touch the x-axis. This function just gets closer and closer and closer, microscopically closer, but it never touches. Y can never, ever equal 0 because there's no exponent we can put with that 2 to make this y value be 0. We can just get smaller and smaller and smaller. Then we draw a smooth curve. We've already got that. And then let's look at our range. So we know the domain is all real numbers. Like, in other words, we can go to any value on the x-axis. But like I just said, we're never, ever going to touch the x-axis with our curve. So the y values have to be greater than 0. Okay? So it says the range is all positive real numbers. Another way you can write it is y has to be greater than 0. Okay? Anything above 0 is game for those answers. All right, so here's example 3. Graph the functions y equals 3 times 2 to the x power and y equals negative 3 times 2 to the x power, and compare them with just this. Okay? The difference here is we have an a value. Okay? Remember our original function was a times b to the x power. Well, in this case, we have an a of 3 that we put in front of that 2 to the x, and here we have an a of negative 3 that we put in front of the 2 to the x. So let's compare those graphs. To graph each function, make a table of values. We've already done this one in our last example. And then we're going to plot the points and draw a smooth curve. So here's our table. I'm going to let you pause the video if you want to. If you don't have the table on your notes, pause the video, fill all this in, make sure you understand how we got all of this. Okay, and then we're going to graph. Notice I've got them by color. So y equals 2x is this first curve. We did that in the last problem. Notice how the red curve, where we have the 3 in front, it curves at an even steeper, quicker rate. Because we're taking that 2 to the x power and we're even making it increase more quickly by putting that 3 in front of it. And then the negative 3 in front graphs a mirror image of the positive 3. So we have kind of a reflection. But this time we're going downward. Okay? We're still getting close to that x-axis, but we will still never, never, ever touch it. All right, here's the deal. Here's how you compare. And so if you want examples when it asks you in homework or tests to compare, here is what you are supposed to say. Okay? Here are perfect examples of the comparisons. Because the y values for y equals 3 times 2 to the x power are 3 times the corresponding y values, the graph is a vertical stretch. In other words, it increases at a much faster rate. It's a vertical stretch. And because the y values for y to the negative 3 are negative 3 times the corresponding values, they're a vertical stretch with a reflection in the x-axis. So I know that's a lot, that's very confusing, but just think of it. It's stretching and reflecting, okay? So just kind of think about what it looks like, and then kind of describe the looks of it compared to the original graph. All right, that's it. You can bring your notes to class, bring your questions, and I will see you for your assignment tomorrow.